everybody. Right, most of you know me, but for those of you who don't, I'm Edward Tayton. I'm one of the HIP Fellows here, and we've been asked to give a summary of some of our research that we've done up to this point. I've been affiliated with a couple of universities in the past, and now I'm working here at Bournemouth University under Professor Middleton. And I'm just going to run through some of the work that I've been doing between 2007 and 2016. There is some more, but I've just highlighted the more interesting things. This is some of the early work I did, where I was looking at the osteology of femoral anteversion. I was comparing it between quadrupeds and bipedal motion in humans. And the thing that I was really sort of the take-home message from this was that the anteversion angle that you get that quadrupeds have is more in terms of reducing the turning moment at the neck shaft interface for vertical forces, whereas with humans, because we walk with our femurs straight rather than a flexed position, our anteversion angle is more to reduce the turning moment for the force in the AP direction. So that's what that was about. I went on to do a master's degree in Cardiff, working with Sam Evans and Daphne O'Doherty. And the thing I was looking at there was the different stress shielding effects of different implants. I had a flexible implant made of carbon fibre reinforced plastic, and I compared that with an implant that was exactly the same shape but made of titanium, and looked at the stress shielding effects. This is just two of the implants. The one on the right is as you face it, the left is the titanium one, the one on the right is the carbon fibre reinforced plastic one. So we set up a jig here which was mimicking static forces on a proximal femur of an average weighted adult male. We used digital image correlation to look at the stress shielding effects here, and we're most interested in the calcar area, which is where you usually stress shield predominantly. This is an example of some of the images that we were getting. The force on the right, the picture on the right is a normal femur, and the picture on the left is a femur which has been implanted with the titanium implant, and you can see it's much more purple in this area, which basically means that the force going through that part of the femur is a lot less. I did this pictorially, and you can see that the bottom graph here is the forces going through the calcar of a normal femur. The middle line is the one in the carbon fibre reinforced plastic one, and the top line is the titanium one. So you can see the carbon fibre reinforced plastic implant much more closely mimics the natural femur than the titanium one. So you could surmise that it was going to lead to less stress shielding at a later date. The reason the gap's bigger here in the proximal area is because there's a little titanium stem in the carbon fibre reinforced one, and that's why it behaves like the titanium one in the proximal area. So then I went on, I did a PhD in the University of Southampton, and this was the sort of rather confusing title of my PhD, Novel Approaches Towards Successful Implementation of Tissue Engineering Strategies in Impaction Bone Grafting. What I was essentially doing, I've got a little sort of summary slide here of where my work fitted into tissue engineering, really. So I was looking at producing synthetic bone graft that was osteogenic, and also osteoconductive and osteoinductive was where I was going to use. And even though I was looking specifically at impaction bone grafting, the technology I was hoping to create could actually go back here, and it could be used for lots of other things such as trauma and fracture non-unions. It could all sort of feed back into this whole circle. So there we go, the overview is to produce a synthetic osteogenic allograft substitute. I was looking at three key features. One was trying to reproduce the mechanical characteristics of normal bone graft, looking at whether it was biocompatible, whether or not stem cells I could grow, I could put it in and it would be osteoconductive to stem cells. And then I was also going to incorporate stem cells onto the graft to see if we could actually get osteoinductive bone graft as a result of that. I looked at it in vitro in the lab. I did small animal testing in mice, and then I went on to do large animal testing in vivo as well, which was in a sheep model. So how did we decide the polymers we were going to look at? We wanted to use polymers. There's thousands available. They differ in molecular weight as well as type, and just changing molecular weight makes a massive difference in how they perform, so it's very difficult to narrow it down. even at the start. There'd been previous translational success with these 3 polymers here, and so we chose those as our starting points, and then we were going to look at high and low molecular weight forms of each of those as well, to see if we could find one that behaved most like bone. From a biocompatibility point of view, we got our stem cells from human donors, from intramedullary sources, from patients undergoing total hip replacements. We took the cells at that point. We grew them up in the lab here. This is what they look like when they've been growing in tissue culture plastic for a couple of weeks. You've got thousands of them available. From a mechanical testing point of view, we worked up a rig that was going to allow us to look at milled allograft under different forces, and check our own composite to see if we could get it to behave like milled allograft. And this model is a model that Doug Dunlop had created to mimic the forces that go through impaction bone graft in a proximal femur after impaction bone grafting procedure. This is an example of some of the results that we got from the early polymers we were looking at. The allograft control is the black line here, so anything underneath the allograft control on this slide is something that's too weak really to act as a bone graft substitute, but anything higher than the line is something that's a potential candidate, so we could immediately rule out polycaprolactone. In the early stages, left us with high and low molecular weight polylactic acid and polylactic co-glycolic acid is what PLGA stands for. This is an example of some confocal microscopy. This is very clever 3-dimensional microscopy where we've stained the stem cells bright green after they've been growing on the polymers for a couple of weeks. And as you can see, different polymers are much better at growing the stem cells than the other ones, and so that's polylactic acid and that's polycaprolactone, which isn't very good from a biomechanical point of view. So we're sort of narrowing down what's going to be a good graft to use for translational uses. This is an example which basically is a scientific way of looking at that last slide. A WST assay is a means of measuring cellular activity, and again you can see that high molecular weight polylactic acid, there's a definite benefit in terms of growing stem cells on that. So if you look at it under electron microscopy, this maybe gives you some idea as to why polylactic acid is better at growing cells, and just based entirely just on surface roughness, where B is the polylactic acid there, high molecular weight one, whereas that's an electron micro. The top image there is an electron micrograph of normal cancellous bone. So we went on from this and tried to get the polymers to even more closely represent cancellous bone. So one way you can make a porous polymer, these polymers at the start were solid, and one way you can make a porous polymer is by using supercritical CO2 foaming. So it's quite an easy concept here. If you think of CO2, you have it in a hard form when it's frozen, and then when that melts, it goes into dry ice, and you see the smoke that you get in pot concerts and stuff like that. So there's no third phase. Water has 3 phases. It has water, ice, and steam. So CO2 at normal ambient conditions only has 2 phases, but if you heat it up and pressurize it, you get the third phase out of it, and that's called a supercritical fluid. So that's where it falls into this gap here. So the good thing about that is you can put your polymer into a jig, you can pump in CO2 gas, you can pressurize it and heat it a small amount, and it will turn into a supercritical fluid. Then as you let the gas out, it will turn back into a gas again, having dissolved the polymer, and that will then bubble through the polymer as it comes out of phase, and that will lead you to develop a porous structure. So that's the way we made our our scaffolds, and so these are the 2 examples of high molecular weight PLGA and high molecular weight PLA, and this is it after we've supercritically foamed it. So as you can see, it looks a lot more like trabecular bone. This is an example of what the pellets look like at the top pictures after they've been foamed. And so this is again confocal microscopy of these polymers having grown cells on. You can see that they're absolutely flooded with cells when you do this, so they grow a lot more. This is what it looks like under micro CT. We went on to the next stage as well. So the 2 images on the left there are porous polymers foamed, and the ones on the right are where we've also foamed them, but we've added hydroxyapatite to them as well, so we've now got a composite foamed polymer. So we compared both of those, and as you can see, they all acted pretty they were all stronger than bone when put in the mechanical rig, so they were all quite good candidates in terms of mechanical stability. But when it came to growing stem cells and actually inducing those cells to turn into osteoblasts, the PLA was much better than the PLG. So ALP is a measure of osteoblastic activity, and so we had high activity on both of our PLA polymers, highest on the hydroxyapatite composite, and the two PLGA polymers didn't really stimulate the stem cells to turn into osteoblasts. So from this, we thought high molecular weight polylactic acid with hydroxyapatite is probably the best candidate to translate into animals. So we went on to do it into mice. So we took some mice, we put the polymer, as you can see here, this is just the scaffold subcutaneously in the mice, and this is a micro CT of the polymer after 6 weeks subcutaneously in the mice, and you can see there's lots of neovascularization in the polymer, and this stuff in the middle is new bone. So that was quite effective. So we took this on, we put it into a sheep model. So we took the stem cells from the sheep iliac crest, we grew them up for 2 or 3 weeks in the lab, we seeded them onto the stem cells, then we reimplanted them back into the sheep. That's us just anaesthetising the sheep there. So this is the model we use. We use a femoral condyle defect model, so we drilled a hole in the femoral condyle, packed our seeded stem cell, our seeded scaffolds into the condyle, into this region here, and left it there for 3 months. Came back at 3 months, euthanized the sheep, took the femoral condyles out. This was the defect after 3 months in situ. We tested it against normal mechanical bone on each side, and we tested it in 2 sites afterwards. This is some of the results we got from that. So we did it with defect alone, scaffold controls, and scaffold with stem cells. Strangely enough, the scaffold with stem cells did not work as well as the scaffold on its own, which you could take negatively, but actually if you think about it, because we had a composite polymer which was osteoinductive, it was actually a very effective way of getting the bony ingrowth in the area. So that's quite an interesting finding. This is micro CT of the defects after the 5 weeks, and so this is the polymer with stem cells, and there's bits of new bone in there, but this is the polymer with no stem cells on it, and actually it's almost, after 3 months in the situ, it's almost filled the gap with normal trabecular bones. So it's quite interesting, really. That was as far as I got with that project. This is some histology of the same thing, and this is a bit of hydroxyapatite here from one of the scaffolds, and you can see that there's normal bone that's grown round there. It's been stimulated for those stem cells to differentiate into osteoblasts, and it happens predominantly around the hydroxyapatite bit. This is another sheep model I did. This is with James Smith, who's one of the other knee fellows here at the moment. So we went on to, this is a binary blend polymer, so rather than just using one polymer, we mixed 2 polymers and tried to get the beneficial effects of each polymer in a mix. This time we did a femoral midshaft defect model where this was about a 3.5 centimetre gap that we cut out of it, put X-fixes on the sheep and left them hopping around the field for 3 months with X-fixes on, and our scaffold in the gap there as well. We got okay results from this. So this is the empty defects, the controls. You can see the way scaffold alone and scaffold and stem cells, although this is most of our scaffold left here. We got some decent rebone, but it wasn't enough to bridge the gap after the 3-month period. That was published. So there was some other little projects that were sort of side projects that we went through at the time. We looked at the results of setting bone cement on skeletal stem cells in our constructs, and looked at what distance the heating effects of the cement affected the growth of the cells in the construct. And you can see here, this was a sort of how far the heat propagated. So at the cement bone interface, you got 75 degrees of heat rise, but you only needed to go 5 millimeters away, and the heat rise had already become negligible. So that was quite interesting to know how far you damage bone when you put cement into it. This is that pictorially. So this is the stem cells at the cement bone interface, and the red cells are dead cells, and you can see the difference 1 centimetre where there's still stem cells all over everything, but at the cement bone interface you've killed most of the stem cells there. That's just a graph to represent that. This was another project we did, which was a sort of offshoot from the main project. We looked at the different toxicities of skeletal stem cells, of local anaesthetic on skeletal stem cells. Somewhere this could be translated as something like microfracture in the knee. So if you microfracture in the knee, you're stimulating skeletal stem cells, trying to get them to differentiate into cartilage, and then you go and fill the knee up with local anaesthetic at the end of the procedure, and you go and kill all the skeletal stem cells. So we looked at the different toxicities of 3 local anaesthetics in different concentrations, and you can see here that levobupivacaine, which is an isomer of bupivacaine, has very little effect on stem cells, but both lidocaine and bupivacaine basically kill off nearly all the stem cells. And this is just some confocal microscopy showing the same. So when you look at 50% concentration of lidocaine, you've virtually killed all those red cells are all dead cells. You've killed all your cells. When you do the same with levobupivacaine, there's very little cell death whatsoever. So if you're doing microfracture of the knee, I strongly recommend you put levobupivacaine in afterwards as your local anaesthetic. That's the same, just a histological staining slide. And that's it. Is full time.